Hi, my name is Kevin Vinsen. I'm a Senior Research Fellow at the International Centre for Radio Astronomy Research based at the University of Western Australia. I'm here to tell you about machine learning and how it can be used on the outputs of HPTLC. So let's start with the definition. What is machine learning? Machine learning is the discipline of artificial intelligence that allows machines to automatically learn from data and past experience to identify patterns and make predictions. Machine learning is a very hot topic at the moment. I'm sure you've all used tools like Apple Siri, Google, Amazon's Alexa. All of these use machine learning. So let's talk about the two types of machine learning. Supervised machine learning requires labeled inputs and outputs. So effectively, we teach the computer, this is an apple, by showing it an apple and giving it a label. Unsupervised learning is training models on raw and unlabeled data. So the main difference here is between having labeled or unlabeled data. Let me explain a little further. Supervised learning requires labeled input and output. So supervised learning is able to classify unseen data by establishing categories. A model is developed by showing the machine learning algorithm various examples, so it learns what that looks like. And then when we present new data, it's able to make a prediction on what it is. Now, what the system does is go through many iterations to do this. This is what most machine learning systems are used for. Now, for HPTLC output, this actually has very limited usage. The main reason being, you've got eyes. You can look at the tracks and you can see where the bands are. Unsupervised learning takes raw data and then tries to find patterns and group the data together. So in the example here, we're grouping birds, fish, and animals together because they have similar traits. Now, this could be used when we don't know what the real sample of the data is. We have no major control. Things like honey data, where you can't tell where the bees have gone. We have no idea what trees the bees go to collect pollen. So the first thing we need with machine learning is good, consistent data. For HPTLC, this means regularly calibrated machines operating in a controlled environment with a controlled temperature and humidity. Machine learning suffers from classic GIGO problems. Incorrect or bad input data results in incorrect or bad output data. Now, the first thing we need to think about is what we see as color. The human eye has three kinds of cone cells that are sensitive to light. Short, which is really looking sort of in the blue, medium, which is looking in the green, and long, which is looking in the red. Now, the way we actually see color is the amount of light that hits each of the various types of cone is then integrated, and we perceive that as a color. But we're actually what we're really seeing is a wavelength across a whole range. Now, in 1931, the CIE, which is the International Color Forum, came up with a model. Around the edge of this graph, we have the frequency, the wavelength in nanometers. These are spectral colors. So these are the pure colors that we can see in the spectrum. And this is an astronomer, what we use for most of our work. All the other colors you can see there are made up of these colors. Now, this is where we have a problem, because what we need to do is model this onto our eyes, which basically use red, green, blue, RGB. And there are literally dozens of ways this is modeled. So there is no consistent way where colors are done. Now, the most common form is the sRGB, which is the black dotted line. So all of those greeny colors to the top left, we don't actually see in sRGB. The corners are the main points of red, green, and blue. So what you're seeing is a trick. So if you move from one color scheme to another color scheme, so if you take an image, put it into a Word document, and then maybe generate an Adobe PowerPoint from it, or pass that image into Adobe's Illustrator, it can change the RGB palette underneath it. So what you're seeing isn't necessarily what's real. All colors on the line from 500 nanometers to 600 nanometers can be made by mixing 500 nanometer and 600 nanometer light at different intensities. This means that what we're seeing is actually two different spectral peaks, giving us a whole range of colors depending on their amplitude. Another method that we can make a color is by taking the line from 500 through the white spot. By mixing 500 nanometers and white light, we can make all of the colors that you see on that graph. So again, what you are seeing is your brain being clever and tricking you. Now, it gets much worse when we start adding macadam ellipses in there. These are areas there where the human eye cannot distinguish colors. So as you see from these two lines, the large ellipse near the 0.7 on the y-axis, all is the same, but we can make the colors from that by having a peak at between 480 and 490 nanometers and 540 nanometers, or from a peak of just less than 520 to 600. Which is it? Now, when you are working with a normal HPTLC, you'll see the color, but you're comparing it against other colors. That's fine. When we're working in an unsupervised space, we need to know where the spectral peak is, because the two different greens could well be two different colors and two different chemicals giving spectral responses. So spectrum is a better solution. RGB values obtained in conventional systems often have different meanings depending on the device characteristics and the color processing. Different spectral peaks can give the same RGB color. And in the long term, when we have to archive all of these images into databases, we need to have all of this color information. And the RGB signal depends on devices, illumination sources, pre-processing steps, which are just not recorded. Whereas the spectra is the spectra. It is always the same. Now, the downside of that is we're suddenly increasing hugely the amount of data that we have. Then again, machine learning can come to our rescue again with autoencoders. This can reduce thousands of input data points into a much smaller latent space. And from that latent space, rebuild the original data. Now, this is used as a way of reducing data in the same way that things like PCA work, but it is much more sophisticated than PCA. What we can do with this, we can train with augmented data where we shift things in the X and Y axis, or the retention factor and the AU, and then train it with actual results. So we're able to then correct for noise in the system. We're able also to correct for drift, so you don't need to use dynamic time warping. We can also deal with nonlinear relationships, which is something PCA cannot do. And finally, I'd like to talk about Gaussian mixture models. Now, this is a clustering model that is far better than k-means and dendrograms. It accounts for variance. Now, k-means and dendrograms are what we call hard cluster. You are in the cluster or you're not. And they're also circular. With Gaussian mixture models, it's a soft clustering approach. This means you're given a probability of whether a value is in a cluster. It's also elliptical. So it can be elliptical in n dimensions. So here's an example. the circle is in cluster A, possibly at 60%, or cluster B at 40%. But you can see we can also do sigma values where we show that whole set by moving it out. So let me show you some outputs from a honey example. Now this was reduced using an autoencoder and clustered using Gaussian mixture models. So you can see how well the data tends to cluster together. The different colored blobs are what the beekeeper reported the honey to be. And we can see that some of them are not. We can also extend the ranges of them. So I've moved clusters 3 and 7 out to 2 sigma. So we're able to see what elements are within that grouping. And we can also look at individuals and see that this particular honey has a very high chance of being in cluster 1 and very small chances of being in cluster 3 and cluster 6. So, conclusions. Machine learning provides excellent tools for dimensionality reduction, clustering data in a probabilistic way, and it can correct the data to some degree. But it is only as good as the data it is given. Thank you for listening, and I hope you found my talk entertaining.